Such approximated depth chain can be computed by a pre-analysis, that is a coarser and quicker static analysis than the main analysis. Okay. Then how do we design such a pre-analysis? In general, any sound approximation of the main analysis is eligible. Okay. So for example, in our case, simply using the flow insensitive version, okay, is also a reasonable choice. Okay. So suppose we have this color connection that further abstract the main analysis to the pre-analysis. As you can see, this pre-analysis is the flow insensitive version of the main analysis. That can be a reasonable choice for a pre-analysis. Okay. Here, an important notice is that the relationship between the pre and the main analysis. Okay. Which means, what if the pre-analysis is too imprecise? Okay, then what happens? The important thing is that the pre-analysis, if the pre-analysis is a sound approximation of the main analysis, then the precision of the pre-analysis does not affect the final precision of the main analysis. It only controls the sparsity. Okay, if you have a very poor pre-analysis, then your sparse analysis, okay, will be almost as the same as the main analysis, which means very slow and require a lot of memory. But if your pre-analysis is very precise, okay, then you have enough sparsity. You can exploit plenty of sparsity, but your pre-analysis may be very costly. Okay, that is the design choice. But we should be a bit careful when we define the approximated depth and use set using the pre-analysis result. Okay. To be safe, okay, the approximated depth and use set must satisfy the following conditions. Okay, here let's take a look at this one by one. The first one is a bit trivial. The approximated depth and use set by the pre-analysis, okay, must be over approximations of those of the original ones. Okay, it's somewhat trivial and intuitive, right? The depth set by the pre-analysis and the use set by the pre-analysis must subsume the ideal one. Okay, must be over approximation. The second one, which is a bit more important, is that all spurious definitions from the pre-analysis or spurious definitions by the pre-analysis must be included in the approximated use set. Okay, what does that mean? Because the pre-analysis is an over approximation of the main analysis. Okay, because of that, the approximated depth set, this one, okay, may contain some spurious memory locations, okay, that are not actually defined during the main analysis. Okay, but because of the approximation of the pre-analysis, it contains some spurious definitions. That is what I mean by spurious. Okay, this condition says that in this case, these spurious definitions must be included by the approximated use. Okay, that is what the condition say. Okay, we will see what this means later. Okay, and then the approximated depth chain is defined using the pre-analysis result and the approximated depth and use set. As you can see, here we use pre-analysis result and we use approximated depth set and approximated use set. So this approximated depth chain is computable before the analysis. Okay. Then let's see an example that shows that why the second condition is needed. First, Okay, let's see the ideal depth chain, okay, by the original analysis. Okay. Consider this simple program, okay, 3 statement, and each def and use sets for each label. Okay. Here, suppose this variable p, okay, has the abstract memory addresses v and w, okay, in the main analysis. Okay, let's assume that. Then there exists a depth chain for x between the first part and the last label. Okay. Because x is defined in the first label, as you can see here, okay, used in the last label, okay, and the intermediate instruction does not define x at all. Okay. So that is our definition of depth chain, right? Okay. So we can draw this depth chain for x. So as you can see, so this depth chain is correct, which means that the analysis that follows the depth chain, not control flow, okay, will have the same result, okay, with respect to x in this case. Okay, if we compare the analysis result, two analysis results, one is the original version, and the second one is the sparse version, then the result for variable x, okay, in this program will be the same. Okay, in that sense, we say this depth chain is correct. Okay, but what happens if we have approximated depth and use set that only satisfy the first condition, which is the over approximation condition? So as you can see, this D pre and U pre, okay, these two sets are actually superset of the original ones. Okay, as you can see, all of the sets are the same as the original set except for this one. Okay, here is because of the approximation of the pre-analysis. Here we have a spurious element, spurious definition of x. Suppose the pre-analysis computes this spurious information, okay, but it totally satisfies the first condition. Okay, then according to our definition of depth chain, okay, we will have only this depth chain, okay, because x is defined here, okay, and used here and not modified in between. So we have this depth chain. Okay, so this will be missed, okay, because the definition of x from this label is killed by this label. Then what happens? This sparse analysis result, okay, with this depth chain, let us check whether this analysis result have the same result, okay, as the one from the original one with respect to variable x, right? If we just follow this one depth chain for x, okay, then the sparse version does not have correct answer, okay, correct analysis result for this program, right? If the sparse analysis only consider, okay, this edge, then abstract value for x and y at this label, okay, will be bottom, right? Because something is missing here, because no abstract value for x is correctly propagated in the main analysis. Again, in the main analysis, okay, x is defined here, but because of the wrong depth chain, there is no connection from this x to this x, okay, because of this spurious definition, right? That is the problem. So this should be corrected by propagating the previous x, okay, the previously defined x here to the spurious point. Okay, that is the correction. Then this second condition, okay, force this one, because all the spurious definitions, okay, the spurious definitions are also in the approximated use set. Okay. Then you can always have this kind of, okay, bridge. Okay. Again, notice that the over approximation of the pre-analysis, okay, just determines the sparsity, not the precision and soundness. Okay. If you have very imprecise result, the sparse analysis will work as the same as the original non-sparse version. Okay. In this case, if you have more precise pre-analysis, okay, that does not have this spurious depth, then what happens? Then it will have a bigger jump like this. It does not have this one. It will have this big jump. Okay, that will make the analysis much faster. Right. Here I show some practical impact from the original paper of the sparse analysis. And this table shows the characteristics of a set of real-world benchmark. So here, as you can see, the lines of code in C program. So here, this simple gzip consists of 7,000 lines of C program, and some larger program like Ghost script is larger than 1 million lines of code. Okay, and some notable statistics for the program, such as the number of functions and statement, and the number of abstract memory locations. So this table shows the result. Okay, the non-sparse version takes really long time and does not scale to beyond 35 kilolines of code. Okay, it's really unscalable. If the analysis exploits only spatial sparsity, it can reduce the cost a lot. Okay, but as you can see, it still does not scale beyond some moderate size. Okay, and finally, combined with temporal sparsity, it can save the analysis cost a lot. Okay, and finally scalable to millions lines of code. Okay. So let me summarize this lecture. So we learned sparse analysis framework, okay, which is a general framework for reducing the analysis cost while preserving the precision. Okay, which means once you have sound yet unscalable static analysis, the framework automatically derives the sparse version. Okay. Here the key idea is to compute right part at right moment during the analysis based on semantic depth chain rather than syntactic control flow. Okay. The approximative depth chain is needed, and this approximative depth chain can be computed using a pre-analysis. Okay. And the depth and use set from the pre-analysis must satisfy the safety conditions. Okay, that is the sparse analysis framework.